Alright, so this video is meant to accompany my lecture notes. In particular, I'm basically in Chapter 1 at the start, where we're looking at vectors and points and components. So to start with, let's just set the notation up. R2, or sometimes we think of it geometrically as the plane, is something like this: x and y, ordered pairs, such that x and y are real numbers. Alright, so there's a natural correspondence between this set. In terms of what's called a Cartesian product, this is R cross R. Alright, now R3, ordered triples, oftentimes we use x, y, and z for typical labels of the x, y, and z components. Again, x, y, and z are real numbers. And then we'll look some at Rn. And Rn is, well, we could just number it this time: x1, x2, xn, such that all these guys are real numbers. Okay, so this is the context in which we're studying geometry and calculus ultimately, although mostly we're going to be looking at algebra and geometry for a little bit here. Alright, so suppose x and y. So by the way, I sometimes use, well, let me see, I'll put vectors on them just to be more careful. Suppose x and y are elements of Rn, then x equals to y, x vector equals to y vector, if and only if the xj equals yj for all j, 1, 2, n. In other words, two vectors are equal only if they match in all the components. Alright, so that's actually fundamental. The very construction, like this Cartesian product, is designed precisely so that three tuples only be equal if they match in every one of the components. Alright, okay, so this up to now is essentially just definition. Alright, in fact, most of what I'm saying for the moment is a definition, but I'm going to change colors here. I guess I'll go to purple here for a bit. You can also talk about the distance between 2 points. Let's say A and B. So I'm supposing A and B are points in Rn, and that distance is going to be equal to the square root of the sum j equals 1 to n of parentheses bj minus aj quantity squared. Right. Now let me just break out what that looks like. So for like n equals to 2, of course the distance formula for the plane you might remember from like middle school or whatever, b2 minus a2 quantity squared. So like the difference between the components squared added together, square rooted, that gives us the distance. And likewise, for n equals to 3, the distance between 2 points in 3 dimensions, we take the sum of the squares of the difference between the likewise components. So it's just like the 2D formula, but there's just one more term, right, for the z if you like. Alright, so those are our formulas for distance in 2 and 3 dimension, and also for n dimensions. And I would point out on page 12 of my notes, there's like a little picture which shows how you can understand where the three-dimensional formula comes from by looking at triangles and looking at the two-dimensional formula. Just you can actually understand where the three-dimensional formula comes from by looking at a particular picture and thinking about the two-dimensional formula. Now, so I've already said sometimes I'm thinking of the things in Rn as vectors, and sometimes, just to be clear here, A and B were in Rn. So sometimes I'm thinking of Rn as being made up of as points, and sometimes I'm thinking of Rn as being made up as vectors based at the origin. And that's okay, because here's why. There's a natural one-to-one correspondence between vectors based at the origin and points. So if this is the point, A, B, C, right? That point in three-dimensional space, let's say, that naturally corresponds to the vector that starts at the origin, right, and goes out to that point. So the vector, if I want to emphasize that it's a vector, I use these angle brackets, A, B, C. So that means, to me, that means vector. That means it's a directed line segment from the origin out to ABC. Now ABC I'm thinking of as that point in space. So conceptually these are different things, but we'll actually set this equal to that for practical purposes. Now, if you have 2 points in space, right? If you have 2 points in space, you can talk about the, so sorry, it's going to be a lot of definitions for a little bit here, guys. So the line segment, the directed line segment from P to Q, we can write as Q minus P. All right, so this would be the directed line segment. Line segment from P to Q. So P is what's called, let's see here, P is the initial point, and Q is the terminal point, or sometimes P is called the base point. And Q is called the terminal point. Q is where the vector is. So notice that when P equals to 0, we get that P, excuse me, P, I just said P is 0. We get like 0 Q, no one writes this, but you get 0 Q vector just equals to Q, right? So, in other words, we just drop the 0 and we say Q vector equals to Q. But when we do that, that's making use of this picture. I'm a little bit unhappy about this equation I just wrote because I will soon introduce another notation where the symbol without the vector necessarily means the length of the vector. And here I actually mean this is a point, this is a vector. They're both 3 tuples. Anyway, let me stop talking about this. I'm just going to confuse the issue. It's really just we have to get into the problems and you'll see it's not actually a big a deal. You could imagine carrying around like the base point of vectors. So like, suppose this is a vector, right? Directed line segment like that. Here it's based at this point, right? I could move that over to here. Physics people would say that's the same vector because it has the same like direction and length. But other people would say, oh no, that's a different vector because it has a different base point. This one's here, that one's there. Are those different vectors? Well, oftentimes we identify those by something called parallel transport, that we can move the vector around while maintaining its direction. And that's fine in our context. All right, I'm going to shut up about that. So, vector addition. What can we say about vector addition? Let me turn the page here. So, vector addition. Geometrically, it's very simple. We do what? We add tip to tail. So, so if I had a vector, you know, like this one, and I was adding, say, this one, then geometrically the way that works is I draw A. It's supposed to be the same length. That's A. And then I draw B from the tip of A to the tail of B like that. B, right? And then the resultant is this guy. This right here is what we would call A plus B. That's how to understand vector addition geometrically. We just do tip to tail. Now, so another useful example would be something like this. If we had, let's say, vector A, right? And we had vector B. Oh, fine, I'll stick with my color coding is not best. All right, so B, A, and B. Then I can ask myself, what vector would it take to get from the tip of A to the tip of B? And so let's give that mystery vector a name. Let's call it X vector. Like this. What vector would that be? Let me call it X. All right. Well, because of tip-to-tail vector addition, you can see that X, right, plus what? Plus A. Excuse me, I should really say A plus X, but I wrote them. Fine, I'll do it over here. A plus X, right? A plus X, what should it be equal to? It should be equal to, excuse my scribble, it should be equal to B, right? Because that's the same displacement from the origin. If you go this way and then you go that way, it's the same as if you just go that way, right? So A plus X should be equal to B, which goes to show you that our mystery vector X, in fact, is equal to what? Apparently, B minus A. So we can subtract vectors like that too. In other words, what I have, and of course this is exactly the same idea as that, thing we were talking about with the displacement vector from P to Q, right? If I think about point P, right, and if I think about point Q, right, then the vector from P to Q, this guy, is PQ, right? And I said that that was Q minus P, right? But we can understand why that is in terms of this discussion, right? Because the vector out to P, we call P vector. Vector from the origin out to Q, we call the Q vector. And, right, so basically Q is like B, P is like A. In other words, B minus A, which is, Q minus P. So if we identify, points with vectors based at the origin, then we can write equations like this. So I'll try to stick with just writing this rather than writing that. But every so often I write a point without a vector sign, so I'm warning you. Okay. One fun fact: if you were to draw the vectors around any closed geometric shape, the vectors would sum to 0. Here, let me make a funny shape. Like this. All right. It's starting to look like something from Minecraft. Oh well. My apologies. So suppose you had that shape, right? If you were to draw vectors, one after the other, that went around the perimeter of the shape, like this, right? This, and then this, and then this, and then this, and then this, and you were to look at the sum of those vectors, right? I'll give them names here in just a second. But the sum of vectors that are placed like that around a shape, a closed shape, in the plane. So suppose this is like A, B, C, D, E, F, G, H. So A plus B plus C plus D plus E plus F plus G plus H is right back where we started again, right? So the sum of all those guys is what? It is 0. Actually, it's the 0 vector, to be careful. The sum of vectors should be a vector again. All right, this is one of the major things that you should notice about vectors, is that when we add them together, we get another vector. All right. Now, so this is geometric vector addition. The algebraic definition of vector addition is much simpler. So definition, if I have v and w in Rn, right, two n vectors, then we can define the vector addition v plus w by telling that the jth component of that is the jth component of v plus the jth component of the w. And if I take, by the way, c times v, I haven't talked about this yet, but scalar multiplication of a vector, well, we just do c times vj. And this is for all j, 1, 2, n. In other words, we can define vector addition and scalar multiplication component-wise, just like that. So I've already discussed geometrically like what vector addition means. Scalar multiplication is just what it sounds like. It like rescales the vector. So, you know, if I was to say take v and then look at 2v, it's like a vector that's the same as v but twice as long, right? So like I'll draw over here in the margin. If this is v, right, then 2v would also be v plus v, all right? So 2v is also v plus v, but it's roughly that, right? On the other hand, if I was to look at, like, say, minus v would be the opposite direction. That's how that works. Negative numbers flip it over 180 degrees. So we should talk more about 180 degrees, shouldn't we? Before I do that, though, let me just say a word or two about components. Definition. If we have a vector in the plane, let's say AB, then the scalar components of the are A and B respectively. In particular, A is what? This is the x component. And B is what? Is the y component. In contrast, the vector components of the are A0 and 0b, respectively, for the x and the y. Now, so it's nice to have a like a clean notation for these vector components in terms of the scalar components. Like another way we can write this is a times 1, 0. All right, and we could write this as b times 0b, 0, 1 rather. Okay, and this little vector here by definition is x hat. It's the unit vector in the x direction. And this little vector is y hat. So let me just, at the risk of boring you, draw a picture again. If we have this vector, here, I'll make it brown this time, vector v, right? We can write down here, this vector would be a x hat. That's this piece. And then the other piece, the vertical piece, would be b y hat. So as you can see, like we can think of the math here algebraically, or we can think of it geometrically. So geometrically, it's just this picture. Algebraically, we've got v is a comma b, right? But we can break that up and we can say, well, that's a comma 0 plus 0 comma b by the definition of vector addition. And that's like a times 1, 0 plus b times 0, 1. which is ax hat plus by hat, right? And so I'm doing this discussion in the plane, but likewise for R3, we can take a vector v and we can break it up into ax hat plus by hat plus cz hat, and I'll draw the picture. I'll try to draw the picture. Hopefully I'm within frame. We'll find out in a second here. So like, you know, you got a vector out from the origin, and I'll call it v again, and suppose it's ABC for the sake of discussion. Well, you can break that into three pieces, right? Like your ax hat, which is going to go along this direction, like so. And then you've got your like by hat piece, which I'll do in blue again. It should be something like this. And then you also have the piece which jumps up off the xy plane, like that. So here's your CZ hat. All right, now that was supposed to join. But here, notice that the meaning of x hat, y hat, and z hat has changed a little bit. Now I mean x hat is 1, 0, 0, y hat is 0, 1, 0, and z hat is 0, 0, 1. So this is the notation I use. Other books will use I, J, and K boldface rather than x hat, y hat, z hat, but as we go on in this course, you'll see why I use x, y, and z. It's because, I mean, other people, like I said, they would use like I hat, J hat, and K hat in place of x, y, and z. I use x, y, and z hat because it naturally transitions to curvilinear coordinates later, and I just think it's a better notation. It also is partly because I was raised by physicists, and that's the notation they use. Actually, my parents are doctors. I'm talking about education. I was not raised by physicists. I was raised by doctors. Okay, now let's go on here. Let me just change my page of remembrance. Okay, so let's talk about the length of a vector. So the length of a vector we could understand to simply be the length of from the origin, right? So of the point, distance from the origin to the point that the vector points to. You could think of it that way, but I'll just state a definition for us. Length of vector at length of vector A, and I'll do it in n dimensions, is, and here's the notation, double bar A, double bar again, like that. It's equal to the square root of a1 squared plus a2 squared plus plus an squared. So of course that simplifies back to the distance formula where one of the points is the origin. Now we also use the notation a without the vector is the length. This is the so-called magnitude. So magnitude and length of a vector are the same. The magnitude is the length is the magnitude. Okay, so this also brings us to another definition. If A is non-zero, then the unit vector in a direction is simply, okay, simply is not really part of the definition, that's just me being stupid. A hat is 1 over the length of A times A. Okay, so that's the definition of unit vector. So what does that mean? Well, that immediately means that you could also say this. You could say that the vector A is equal to the magnitude times the unit vector A hat. What that means is that any vector can be written as the product of its magnitude and its direction. So the direction is generally a vector of unit length, which points in the direction of the vector. So that's a very important principle. Now, when we're in 2 dimensions, there are all kinds of special things that happen. Let's talk about n equals 2 for just a little bit here. Because in n equals 2, in 2 dimensions, we also can use the standard angle to characterize how the vector is pointing. Okay, so n equals 2, if I draw the axes like this, x and y, right? And if I picture a vector, here, I'll put in the first quadrant to start with. Let's say A, and I'll use AX and AY for the labels of the components this time. Sometimes I use 1 and 2. Sometimes I use sub x, sub y. You know, there's different choices. The angle, the so-called standard angle, is measured how? It's measured counterclockwise from the positive x-axis. So here, theta is the counterclockwise measured angle from positive x-axis. So again, counterclockwise means like that. We used to have these things called clocks. You may remember them. I mean, oh look, I have one here. So clockwise is like this. See, doot, 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 doot. Oh my goodness, what time is it? Anyway, it's the time when the children are quiet is the answer to that question. But so that's clockwise. Counterclockwise would be the other way. So, all right. So counterclockwise angle measured from positive x-axis. And if you look at the right triangle trigonometry of that, you can see something immediately, right? You can see that this, if we drop that down like this distance right here. So first of all, the hypotenuse is the magnitude, which is A. So that makes this A cosine theta. And that makes this over here A sine theta, right? So let's put the geometry together with the algebra, right? There's always an interplay going on here, guys, between algebra and geometry. We need both. The synthesis of these two is analytic geometry, which is the thing we're studying right now. So A is what? AX is A cosine theta, and AY is A sine theta, right? So we can factor that A out by a scalar multiplication, and we've got cosine theta, sine theta. All right, well, it turns out that if you have a formula like this, of course this is also equal to A hat, where A hat is the unit vector, and you can see by comparison there that, in fact, this and that are the same thing. In other words, the unit vector in the direction in 2 dimensions is simply cosine theta, sine theta. So we can get the direction, the magnitude, excuse me, the unit direction vector from the standard angle by doing sine, cosine, sine, and vice versa. So there's a unique correspondence between the direction and the choice of standard angle in 2 dimensions. Just a quick review, because students always have a problem with this. In my experience, maybe not you guys. Let's hope not. I hope not. But just some examples. A quick example. This guy, 1, that has theta equal to, I'll do it in degrees right now. You could do it in radians if you want. 45 degrees. This guy over here, which would be something like minus 1, 1. That has theta equal to 135 degrees. This guy down here, minus 1, theta equals to, what is it, 180 plus 45, 225 degrees, right? And this guy down here, these should all be the same. But anyway, 1 minus 1, this has theta equal to what? Well, 270 plus 45, 315. Or minus 45 degrees. And this equal is a geometric equals, right? It's not like a mathematical, like numbers are equal. These are geometrically identified. Of course, when we're working with angles, we can always add 360, multiples of 360, right? So the reason I draw your attention to this is just in case you guys probably already know and everything, but just a warning. When you're trying to calculate standard angle, right, you got to be careful. You got to think through it. It is only the case that theta is the inverse tangent of like AY over AX. Only true when the x component is positive. The inverse tangent will mislead you in quadrants 2 and 3. So that's just a warning. You got to think through it otherwise. You got to work through the trigonometry there to find the standard angle. Of course, I hope you already did that in your previous course. If you didn't, you know, just that's why I'm warning you right now. Okay, so with that, we move on to dot products. So dot products. Excuse me. Why do we care about dot products? What is the dot product? So I'll give you the definition. Now, if you're looking for more motivation and some discussion of why these things are true and, you know, more about properties and everything else, if you look at my notes, there's plenty there, right? So I'm trying to just stick to the bare bones here for the video, just the bare minimum, in my estimation, for you to have a really solid understanding of vectors and their properties and so forth. Okay, so A dot B is A1 B1 plus A2 B2 plus A and Bn. There is a theorem, a non-trivial theorem, which says that this is equal to A, B, and the cosine of the angle between them. All right, so that is not obvious. This is a theorem, which it takes me a couple pages to really prove in the notes. Here's the picture for that, you know, if this is A, this is B, this angle between them is theta. Okay. And so some immediate applications of the dot product are what? So for one, if we look at A dot A, we get what? We get A1 squared plus A2 squared plus AN squared. And if you look back a few pages, you'll see that that tells us that the length of A is in fact equal to the square root of A dot A. Well, that's a pretty nice formula. If we want to calculate the length, we just take the square root of the dot product of the vector with itself. Another thing we can do is we can solve this equation up here for the angle. See, the angle between two vectors is the inverse cosine of A dot B over AB. This is super useful because this gives us a nice handy way of calculating the angle between two vectors, you know, without actually doing any kind of like actual real hand-to-hand combat with the geometry, let's say. Like, here's a good example of how that's useful. You might want to try to calculate the angle between, like, here I'll do it like this. I'll put the back. So here's a cube. It's supposed to be a cube. It doesn't quite look like a cube. It was supposed to be a cube. It's almost a cube. So what I want to do is I want to find the angle between this back vertical leg, which I'll make it green. So I want to find the angle between this guy right here. Let's call that A. And the the vector which points out to the front corner, like this B. I want to find the angle between those two. Right here, that angle, theta, right? So let's see here. It would be easier if I had something more geometric. So like here is, oh man, I only have that. I don't have enough of these toys. But if you can imagine, this is the cube, right? Here's one leg, here's the other leg. Like you can kind of see that cube. Imagine I have more of these. So I'm trying to find the angle, right, between this diagonal and sweeping up to that back vertical leg, like that. Oh man, my son had a Rubik's Cube around here somewhere. Curses. Sorry. Anyway, we actually don't need props. We can actually find out that angle. So it's pretty simple. It doesn't really matter if this cube has sides of length 10 or 1, so we'll just let it have side length 1. So A, we can look at as 0, 0, 1. B is 1, 1, 1, because I'm just going to put that box at the origin to make our life, as easy as it can be. Again, you can make these any length you like, but notice that if that's A, then the length of A is 1, the length of B is the square root of 3, and we can calculate the angle between A and B. Now, whenever I ask students this in class, I have always had at least one student tell me 45 degrees. But it's not the case. In fact, when you calculate theta, you get A dot B. What's A dot B? 0 times 1 plus 0 times 1 plus 1 times 1. That's the dot product, because I do these components plus these components product multiplied plus these components multiplied. That's the definition of dot product. And then divided by the length of A, which is 1, times the length of B, which is root 3. So we get inverse cosine of 1 over root 3, which you can calculate is about 54.7 degrees, approximately. And so the reason that it's not 45 degrees is actually pretty simple. If you start thinking about it, if you were to look at these two vectors from a top-down view, right? And here I'll introduce another notation, like A is coming out of the page at us, right? So like A comes out like that. That's just A. And then B, I can kind of picture from the top down. It looks like this, right? There's your B. And see, the thing is, this is length 1, length 1, length 1, length 1. But this, in this picture, is length square root of 2, right? So really, if you drew the picture like this, if you could draw the cross section. So right now I'm drawing like, I don't want to clutter up my picture, but I guess I will. So like this guy, right? So this is a vertical slice, like a diagonal vertical slice of that. See, A is here, and B would be looking like this in this vertical slice, right? And that's why it's not 45 degrees, because this is length 1, but and this is 1. This is not 1. This diagonal is actually square root of 2. If you look at the geometry here, so that's why you don't get the angle here being 45 degrees. You get something else. So, yep. All right. Now, yes. I should move on. There are tons of interesting properties of dot products. So, whoa. I think somebody fell out of the bed. Oh, there's no crying. That's good. All right, so properties of the dot product, I'll just talk about a couple of them. One of the key ones is that A dot B is equal to B dot A. So the dot product is what's called commutative. But it has lots of other nice properties. It behaves a lot like the regular product that you're used to. Like if I have A plus B, A dot B plus C, it's A dot B plus A dot C, right? And another main one is if you've got like A dot a scalar multiple, like little c is just a number, then you can pull the number out. So it behaves well in this sense. You can pull numbers out of dot products. That's pretty cool. Now, it has other. So those are what I would say are algebraic properties of the dot product. But there are also. Trying to tell you where that is. Give me a second here. So in my notes, the commutative and distributive and scalar law, these are given in proposition 1.1.12, which is on page 19. This is a good list of important properties. Another one I should probably mention is like, of course, if we take A dot A, it equals 0 only if A is equal to 0 itself, the 0 vector. So the dot product of a vector with itself being 0 is very revealing. It says it's the 0 vector we're looking at. So these are what I would say are algebraic properties. But there's also some what I would say analytic or inequality kind of properties. I'm not sure what the properties of the norm is what I call it. So actually these are not directly properties of the dot product, but they're properties of vector length. And if you look at the proofs of these things, they're largely, they involve the dot product significantly, the proofs that I've given. Because we understand the norm of a vector in terms of the dot product, really. So if I pull a number outside of a vector length, we get the absolute value times the length of the vector. That's one thing. There's also something called the triangle inequality. The triangle inequality says if we take the sum of two vectors and calculate the length of the sum, it's less than or equal to the sum of their lengths. So this is the so-called triangle inequality. There's also something called the Cauchy-Schwarz inequality, which says that the magnitude of A dot B is less than or equal to the product of the lengths of A and B. I spend some effort in my notes to explain why the Cauchy-Schwarz inequality allows us to define the angle between two vectors using the dot product. And I also have I spend some effort in the notes to show you that the angle that we define algebraically using the dot product should in fact be the same angle that we're familiar with geometrically. So I have some argument where I look at like a projection onto a plane and go back to the law of cosines and some things like that. Now, I wouldn't test on that. That's really there for your information. If you're worried about what I'm going to test you on, look at the homework. Understand the homework, and you should be okay. Ask me questions about the homework. That's wise. There's more in the notes than you absolutely need to know. My notes are pretty, they're pretty in depth. Like this proof of the triangle inequality I'm looking at here on the page. What is it? Page 20 here. That's not something I would test directly in Calculus 3. It's above the level of this course. That's there for logical completeness. Okay, guys? So I'm going to go on here. At this point, I should switch gears a little bit here and talk about orthogonality. So what does it mean for two vectors to be orthogonal. So in English, sometimes in everyday speak, we use the word perpendicular. Perpendicular. This is the sort of everyman's version of orthogonal. But what they mean is that they meet at right angles. And so as a shorthand, I use this symbol, perpendicular. All right. And so A vector is perpendicular to B vector, or A and B are orthogonal, if and only if A dot B is equal to 0. All right, so that's the definition. And so if we have a set of pairwise orthogonal vectors is an orthogonal set, a set of length 1 orthogonal vectors is orthonormal. So orthonormal is really nice. It means they're both orthogonal and length 1. So a lot of the sets we're most interested in behave this way. Like, so some sort of low-hanging fruit I should point out. Eventually I'll choose a color. The 0 vector is orthogonal to everything. Like if you take the 0 vector dot any vector you like, right, you get back 0. So the 0 vector is perpendicular to all vectors. So that's kind of funny. Another thing I can tell you is if I take the set of vectors like x hat, y hat, z hat, this is an orthonormal set. Because if we look at x hat dot x hat, that would be like 1, 0, 0, dotted with 1, 0, 0, which is 1 times 1 plus 0 times 0 plus 0 times 0, which is equal to 1. So that means that x hat has length 1. And likewise, y hat dot y hat equals z hat dot z hat equals 1. And you can also check x hat dot y hat equals x hat dot z hat equals y hat dot z hat equals 0. So all perpendicular to each other. So this means that the usual unit vectors x hat, y hat, z hat form an orthonormal set. Now that is super useful because, let me show you something. What's the significance of that? Well, one of the significances of that is that so I will give this orthonormal sets are nice. Let me elaborate on why I say that. Sorry, I lost track of my page numbers. Oh no, I've forgotten to number. My apologies. Let's get back here. So this was 4. So that would make this 5. That would make this guy 6. And that would make our current page 7. All right, so orthonormal sets are nice. Let me show you what I mean. If I have a vector, my apologies, I'm just getting my other paper out of the way here. So suppose we have A equal to AX, AY, AZ, right? You can easily check that A dot 1, 0, 0 is AX. Likewise, A dot 0, 1, 0 is AY. A dot 0, 0, 1 is AZ. Right? So, in other words, we can rewrite A as AX, X hat plus AY, Y hat plus AZ, Z hat, but more to the point, I can look at that instead as A dot X hat plus A dot Y hat plus A dot Z hat. See, you know, this right here, right, says that A dot X hat equals AX. This says that A dot Y hat equals AY. This says that A dot Z hat equals to AZ. So in words, we can select the scalar components by taking dot products with the corresponding unit vectors. So this is a a very nice insight, because if you want to calculate the component of a vector in a particular direction, all you need to do is take the dot product with the corresponding unit vector. Now this leads us to make a more general definition, which is that the projection in the b direction of the vector A, we can do the same thing as we did up here. We can just say, well, that's going to be A dot the b unit vector, and we'll put it in the b unit vector direction. So this basically, if you want me to put it in words, this gives us the vector component. It gives us the vector component of A in the b direction. Right. And so we will find that this concept is geometrically useful when we're challenged to find a part of a vector in the direction of another vector. This is a nice idea to know. Pragmatically speaking, that also works out to the following formula: A dot b vector divided by the length of the vector b squared, which we could write as b dot b times b vector. So if you don't want to write it in terms of the unit vector of b, you could also write it in terms of that, because remember, b hat is equal to 1 over the length of b times b vector. So you can change your hats into regular vectors by picking up a factor of b squared downstairs, but b squared is actually b dot b, and that's why that formula is there. Now, you can see page 26 and 27 in my notes for lots of examples on this and a little bit deeper discussion. I would just also point out that the dot product physically has lots of significance. Of course, we already seen it's the length squared. I will just draw your attention to a couple of other here's a little physical comment. Another thing you might know about kinetic energy, 1/2 mv squared, but that's really v dot v, so the dot product is there. You could talk about power from a force. So you do the force dot the velocity, that gives you the power. And then later in this course we'll talk about flux. So if you take the electric field and dot it with the area in question times the normal vector to that area, this gives us electric flux. And you could write a very similar formula for magnetic flux. Okay. And so, I guess I should draw a picture for the projection too while I'm at it. Like, what's going on here is just this. We got, like, if this is A and this is B, then that projection of A into the B direction it's this guy right here. part of the vector A, which points directly in the direction of B. Just like that. So, all right, well, I'm going to stop this, this right here, and next time I'll pick up with cross products, and thank you.